In this episode, we look at factors and multiples. Our objectives: list all the prime factors of a given number. Write a composite number as a product of its primes and primes in exponential form. Identify the highest common factor HCF of two numbers and differentiate between multiples and factors. Engage. Make a 100 board using the cardboard from a shoebox or plain paper. Complete the prime number sieve. With the exception of 2, color all the multiples of 2. Then do the same for 3, 5, and 7 as shown below. So let's look more closely at the prime number sieve. With the exception of 2, you're going to color all of the multiples of 2. So anything that ends with what? 0, 2, 4, 6, 8, then we're going to color those. So 4 would go, 6 would go, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50, 52, 54, 56, 58, 60, 62, 64, 66, 68, 70, 72, 74, 76, 78, 80, 82, 84, 86, 88, 90, 92, 94, 96, then we have 98 and 100. So all those will be taken out. Then we're going to look for all the multiples of 3, and you will do the same. Then all the multiples of 5. Okay, so the 5, the 15, the 25, 35, 45, 55, 65, 75, 85, all of those would have been gone. But before, remember that 5 could go into any number that ends with what? With 0. So that's based on our divisibility rules, but we would have taken out all of these even numbers before. All right, so once we go through that, it says here all the numbers that can be divided by 2 are in green, all the numbers that can be divided by 3 are in blue. So let's look at this. So 9 would go because it's divisible by 3, 15 would go because it's divisible by 3. Let's look at this. How would I know that 15 can be divided by 3? Let's add the digits. 1 and 5 would give us 6, and if the sum of the digits is a multiple of 3, it can be divided by 3. What about 21? 2 and 1 is 3, therefore 21 can be divided by 3. 27, 2 and 7 would be 9, 9 can be divided by 3. 33, you would have 3 and 3, 6. 37, that can't work, but 39 could work because 9 and 3 would make what? 12, and so on and so forth. Now it says all the numbers by 5, and those are listed in orange, and we would have 5 here, but everything else would be accounted for. All the numbers in purple can be divided by 7, so 49, 77, and so forth. Let's explore. It says make a list of all the uncolored numbers except for 1. So 1, they call it the universal factor, so we're not going to include that. Now this is supposed to give us a list of the prime numbers. Now pay attention to this. Just remember this. There are 25 prime numbers between 1 and 100. So at the end of the day, we must get 25. So let's go. 3, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97. Now let's see if we have the 25 that we need. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 97, making 25. So we have 25 what prime numbers between 1 and 100. So for Explore, it says that we should make the list of all the uncolored numbers except number 1. And please remember that this list will have what? 25 numbers there. Next point. What do the uncolored numbers have in common? Why is number 1 not in the group? And that's the uncolored numbers are prime numbers, so they are not in the prime number group. Now, a prime number has two factors, only itself and 1. So that is what they have in common. All of these numbers have this fact in common, that they only have two factors, itself and 1. Those are the only numbers that can be divided into a prime number without leaving a remainder. So once you can divide that number or any number by something other than 1 and itself, then we know it cannot be called a prime number, because the rule is a prime number must be divided by itself and 1. So take for example 9. 9 is not prime because 1 can go in there, 9 can go in there, but 3 can also go into 9. Therefore 9 is not prime. But 2 is special because it's the only even number that is prime. The only things that can go into 2 are 1 and 2. The only things that can go into 3 are 1 and 3. The only things that can go into 5 would be 1 and 5, and so on and so forth. Select some of those numbers, those are primes, and write the factors for them. For example, 3, 17, 31, 47, and 89. Now remember, for all of these, all we're going to have would be 1 and itself. Now recall that factors of a number are the numbers that can be divided into the number without a remainder. Two numbers that are multiplied to get another number are the factors of that number. For example, P times Q is equal to R. P and Q are factors of R. The factors of 17 are 1 and 17. So these factors are the numbers that you multiply, to get 17. All right, so let's move on now. It says here we're going to use the factor tree to show the factors of colored numbers, and those would be composites. Now, what are composites? Composite numbers have 3 or more factors. So a composite number would have 3 or more factors. The numeral 1 is neither prime nor composite because it has only one factor, which would be itself. So here we have an example of a factor tree. We would start with 24. 24 can be broken out to 4 times 6. 4 is a factor of 24 and 6 is a factor of 24. So we could multiply 4 by 6 to get 24. Now this 4 could be broken out into 2 times 2. 2 2s would give you 4. And the 6 could be broken out into 2 times 3. So the prime factors of 24 would be 2, 2, 2, and 3. So it's 2 times 2 times 2 times 3. It says here, write the factors as a multiplication statement. So 1 times 24 would give you 24. 2 times 12 would give you 24. 3 times 8 would give you 24, and 4 times 6 would give you 24. So those are possible multiplication statements, right? But these are the prime factors. And eventually we'll get to exponents, and there's a special way of treating these when we have 2 more than once, how we are going to treat it, and so on. Explain. List the factors of some composite numbers and identify the factors that are prime numbers. Those are called prime factors. If a number is used as a factor and it is prime, it is called a prime factor. Now here's an example. The factors of 24 are 1, 2, 3, 4, 6, 12, and 24. The prime factors are 2 and 3 because they are prime numbers. Now it says, write composite numbers as products of their primes. So we're going to look for the prime factors. Now, here's the example. We had 24, and 24 as a product of its primes would be 2 times 2 times 2 times 3. Remember the factor tree? All right. The factors are at the base or the bottom of the tree. Now, write the composite number as products of their primes in exponential form. We were asked to do that. Now we're going to use the factor tree to find the prime factors. So we have 54. Now 54, we could say 6 nines would give us 54, but the 6 can be broken out into 2 and 3, and the 9 could be broken out into what? 3 and 3. So at the base of this tree, we would have what? 2 by 3 by 3 by 3. So here it is. 54 as a product of its prime would be 2 times 3 times 3 times 3. So 54 is at the top of the tree, while the prime numbers would be at the bottom here. Now it says, express the numbers as a product of its prime factors in exponential form. So 54 would be equal to what? 2 times 3 cubed, or 3 to the power of 3. So let's go back to this. So notice we have 1, 2, 3. So the base would be 3, telling us what number is going to be multiplied by the exponent, the small one, which is 3, telling us that the number appears 3 times. And here we have that. Find the common factors between two numbers and name the highest common factor. Example, the factors of 12 are 1, 2, 3, 4, 6, and 12. And the factors of 20 are 1, 2, 4, 5, and 20. The common factors are 1, 2, and 4. Let's go. So for 12, we have 1. For 20, we have 1. For both of them, we have 2. We have 4 for both of them. 5 is not common, 6 is not common, 12 is not common. So the highest common factor, the factor with the greatest value, would be 4. Extend. Use online sources to play factors and multiplication Jeopardy in groups of 4. List the factors of 12. 1, 2, 3, 4, 6, and 12. And list the first 6 multiples of 12. So we'd have what? 12 times 1 is 12, 12 2s 24, 12 3s 36, 12 4s 48, 12 5s would be 60. It says list the first 6. We have 1, 2, 3, 4, 5. So we would need 12 times 6. All right. So 12 sixes would be 72, and here we have it. Now it says, recall that multiples are the numbers you get when you multiply two numbers. It's like saying the time table, all right? Now, how are factors and multiples different? Factors are the numbers that can be divided into a number without remainder, and multiples are the products that you get when you multiply a number by another counting number. Apply the concepts of factors and multiples to real-life situations. Here's an example. 30, 24, and 36 chairs are to be placed into 3 separate classrooms. The rows in all the classrooms should have the same number of chairs. What is the highest number of chairs that can be in each row? So they asked us to find the highest common factor. That's what we're really working for. The highest common factor of 30, 24, and 36. So what are the factors of 30? The factors of 30 would be 1 and 30. 2 can go into 30 15 times. 3 could go into 30 10 times. 5 could go into 30 6 times. 24. And when we get to 5 and 6 here, we know that there's no whole number between 5 and 6. Alright, so we'll just stop there. That method is called closing. So we're going to start again with 24, 1 and 24. So those are the outer boundaries. And now we're going to close until we get towards the middle. So 2 could go into 24 12 times. 3 8 would give you 24. And 4 times 6. Now the only number that exists between this would be 5, and 5 can't go. Alright, so let's go with 36. This would be 1 here and 36 at the end. And 2 could go into 36 18 times. 3 could go into 36 12 times. 4 could go into 36 9 times. And 6 could go into 36 6 times. So that's dead in the middle. Now between 6 and 9, 8 can't go in there. 7 can't go in there. So we know we're done. Let's look at the common factors that we have. So the common factors would be 1, 2, we see 3. No, 4 is not common. We see 4 2 times. 6 is common. Look, here we have 6. Alright, so 6 is common. So 6, 9, 10, 12 is not common, 18 not common there. Now the highest common factor would be 6. So we have all the factors listed, and this method is primarily listing. Okay, so we're going to look at the factors, and then we look for the common factors and look for the highest common factor. In this case, it's 6. That's one method of finding the highest common factor. Let's look at another method. We have another method here. So we have 30, we have 24, and we have 36. Let's use prime factorization. 2 can go into 30 15 times, 3 can go into 15 5 times, and 5 can go into 15 1. Let's go. 2 can go in there 12, 2 could go into this 6, 2 could go into this 3, and 3 into 3 1. 36. Let's use 2. 2 could go into this 18. 2 could go into this 9 times. 3 into 9 3, and 3 into 3 1. Let's list these now. So we have 2 times 3 times 5, and this would be for 30. For 24 we have 2 times 2 times 2 times 3, and for 36 we have 2 times 2 times 3 times 3. So look for what is common. 2 is definitely common. All right, no, 2 can't use there again. We have 3 in this line and 3 all the way down. Okay, so we have 3, multiply these 2, and we would say 2 times 3, and this would give us 6. So the highest common factor of 30, 24, and 36 would be 6. That means that 6 can go into each of these numbers. So let's look at it. It says use the factor tree to find the factor of each number, and then find the factors that are common, then select the highest common factor. That's what we did. Let's look at it now, neatly arranged. It says the total number of chairs. We have 30, 24, and 36, and this would be the possible number of chairs in each row, or the factors 1, 2, 3, 5, 6, 10, 15 and 30. This is the total possible arrangement. Then for 24 we could have 1 row of 24, 2 rows of 12, 3 rows, 4 rows, 6 rows, 8, 12 rows of 2, or 1 row of 24. All right. Then for 36, again here the common factors are 1, 2, 3 and 6, and the highest common factor is 6. So it says here the highest number of chairs that can be in each row is 6. Now they set it out like this, and I was able to show you using the same listing method here. Next one, Pat and Mark have the same number of marbles. Mark shared his for 5 friends and Pat shared hers for 6 friends. What is the least number of marbles they have? The number of marbles they have must be able to be shared evenly in 5 and 6 sets. Numbers that can be shared in 5 sets are 5, 10, 15, 20, 25, 30, 35, and so on. And numbers that can be shared in sets of 6 are 6, 12, 18, 24, 30, 36, and so on. The lowest common multiple is 30. So the least number of marbles they have is 30. Let's see if we can set that one out. So one person has sets of 5 and the other person has sets of 6. So this would be what? 5, and we're looking for the multiples of 5 and the multiples of 6. So 5, 10, 15, 20, right? 25, 30, 35, 40, 45. Let's fix this one. 45, 50. All right, let's stop there. 6, 12, 18, 24, 30, 36, 42, 48, 48, 54, and 60. Now we're going to look for the lowest common multiple, because these are multiples of 5 and these are multiples of 6. The lowest common multiple here is going to be 30. So 30, the LCM here is equal to 30. So they're asking us what would be the LCM of 5 and 6. So LCM of 5 and 6. So let's start with our lowest prime number 2. 2 cannot go into 5, so we'll write back 5. 2 can go into 6 3 times. Okay. We have no more even numbers, so we're done with 2. Our next greatest prime would be 3. 3 can go into 3 1. All right, so 3 can't go into 5. Write it back. It can go into 3 one time. Let's now go with 5. 5 can go into 5 one time, and we'll write back our 1. Now what we typically say is draw our what? L on the outside, and we're going to write LCM. Notice we have this L, and we're going to multiply everything outside. You know, anything multiplied by 1 will remain the same. So it will be 5 times 3, which would be 15, and 15 times 2 would give us 30. So that's the same as saying 2 times 3 times 5. 2 3s would be 6, and 6 times 5, that would be equal to 30. And because of the commutative property of multiplication, we could say, as before, 5 times 3 times 2, 5 3s would give us 15, and 15 times 2 would give us 30. So the LCM of 5 and 6 would be what? 30, as stated before using the listing method. So one method is listing, and the other method here we use was finding the what? Primes. And you know, we call this prime factorization. Evaluate. Number 1, circle all the prime numbers in the group below, and we have a list of numbers here. So we have taken those numbers and we have place them on our board or whiteboard. And now we're going to see the steps that we need to use this prime number sieve. So step 1, we need to take out all the even numbers. Remember that 2 is the only even number that is prime. So we're going to look for that and we're going to take out all the even numbers. So 4 is out, 6 would be out. 28 is another even. 28 is up this side. Let's see if we can. Yes, good. So 28 is here. Then 42, this is even, and 60 is even. I don't think we have any more. So the next step now would be to take out all the multiples of 3. Now 6 is gone already. So 9 is a multiple of 3. 15, 3 5s, 15 is a multiple of 3. 21 is a multiple of 3. 3 7s, 21. 3 9s, 27. So that takes care of that. 33, because we'd use 3 times 11 for 33. 51. How do I know 51? Because the sum of the digits must be a multiple of 3. Now look at 15. 15 is 5 and 1, and 5 and 1 would be 5 and 1 is 6. Again, 51 here is 5 and 1 being 6. So that also is a multiple of 3. Let's see which other one we would have. 63. Yes, 63. Because 6 and 3 would make 9. So that's a multiple of 3 as well. 81. 81 is a multiple because 8 and 1 would make 9. So we're going to take out 81. And 93. 93 is a multiple because 9 and 3 would make 12. And let's see, 105, we'd have to take 105 out as well, because adding this together we would get 6, and that would make it a multiple of 3. Next up, we're going to take out all the multiples of 5. All right, now remember that 15 is already gone from the first line. Okay, so let's go through. So we have 25. We can take out our 25 here. Let's go to the next line going across. Anything that ends with 0 or 5 we can take out. So 35 could come out. 35 could come out. Any other ending with 0 or 5? 60 is gone already because that was even, and we dealt with those first. All right, so we go 95. All right. 95 is now gone. Let's go now to the multiples of 7. Do I see any multiples of 7? No. So I'm going to keep this 7 here. Okay. So I'm going to keep this 7. So let's go now then to the multiples of 11. Let's go. So we're going to keep our 11. Okay. Any other multiple? 22 not there. 33 is gone already. Next line. 77. 7 times 11 gives you 77, so we'll take this out. Let's go 99. 9 times 11 will give us 99, so 99 is out as well. Let's go. We missed this one, 57. 57 is a multiple of 3 because 5 and 7 would make 12. So this one is gone. So 57 is out. Let's go then now to 69. Same setup because 6 and 9 would make 15. 87, same setup for 87 because 8 and 7 make 15. So 87 also has to go. let's go to the multiples of 13. 13, multiples of 13. So we're going to keep our 13 if it's there. No 13 is there. Keep the 13. 91 is a multiple of 13. 91 is really 7 times 13. 13, and we multiply that by 7. 7 threes will give us 21, right? 1 carry 2, 7 1 7, so 91 is a multiple of 13. So we have to take out this because it's a multiple of 13. Do we have any more left over? All right, so let's look at what we have now. So 7, 11, 19, 23, 29, 31, 37, 59, 61, 67, 71, 89, 97, and 101. Those should be the prime numbers in this group that was given. And guys, this is just one of those things that we just have to practice over and over. And remember once more that between 1 and 100 there are 25 prime numbers. So once we know that, if we set it out on paper and we search for them and we see less than 25, then we know that we're missing some, and we just have to go over the steps. Look for all the even numbers. You're going to keep only 2. Then you go to the next prime number, which is 3. You're going to take out all, keep 3 and take out all of the multiples of 3. Then you move to the next prime, which is going to be 5. You keep 5 and take out all of the multiples of 5. Then you go to 7, keep 7 in your list and then take out all the multiples of 7. Then you go to 11, keep 11, take out all of the multiples, and you keep doing that until you get 25 prime numbers between 1 and 100. So number 2 says now that we need to list all the factors of each number. So we have 23, 35, 42, 57, and 72. Let's do that. So the first one is 23, and the only factors would be 1 and 23. All right. Then we go on to 35. Let's look. 1, and we have 35 on this side. 2 can't be multiplied. 3 can't be multiplied. 5, and then what would give us 35? 5 sevens. So 1 5. Okay, so this would be 1 times 35. 5 times 7, and of course 35 times 1. So those are the factors that are there. Let's go to 42. So if we were to write this out, then let's complete this. Then it would be 7 times 5 and 35 times 1. These are all the possible multiplication scenarios you could use to get the 35. So let's go now to 42. So 42, we have 1 over here and 42 there. Because it's an even number, we know 2 could go in there, 2 could go in there 21 times. All right, 2 could go in there 21 times. Then 3 could go in there. 3 could go in there 14 times. 3 could go in there 14 times. Yes. 6 could go in here 7 times. So we have 1 times 42 give you 42. 2 times 21 would give you 42. 3 times 14 would give you 42 as well, right? and 6 times 7 would give you 42. And if we reverse these, we would get the same thing. 7 times 6, 14 times 3, 21 times 2, and 42 times 1. Next one would be 57. And for this is 1 and 57. 57, we know 5 and 7 would make 12, so we know 3 must can go in there, and that would go in there 19 times. This one is always a tricky one to remember. All right, the 3 and the 19. All right, let's put this one side. 19 times 3, 3 nines would give you 27, right? 7 carry 2, 3 ones 3, and 2 would give you 5. This one is something that we just have to remember. All right, so the factors of 57 would be 1, 3, 19, and 57. All right, so 1 by 57 and 3 by 19. So 1 times 57 and 3 times 19. Again, we could do the reverse, 19 times 3 and 57 times 1. Okay. Last one is 72. And this is going to be a long one. 72. 1 into 72 goes 72 times. No, 2 into 72 would go 36. That's a half of it. Now 3 could go in there because 7 and 2 is 9. So 3 can always go into that. And 3 could go into that 24 times. So 3 could go in there 24 times. Then 4 could go in there as well. 4 could go in there 18 times. 18 times. 6 could go in there. There's a rule that says if 2 can go in there and 3 can go in there, then 6 could go in there as well. So 6 could go in there 12 times. 6 12s would be 72. And 8 could go in there 9 times. 8 9s would be 72. And there's no number between 8 and 9, so we know that this is closed and we're done. So the factors of 72 would be 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 36, and 72. So 1 times 72 would give you 72. 2 times 36 would give you 72. 3 times 24 would give you 72. 4 times 18 would give you 72. Let's make a little more space. 6 times 12 would give you 72. And 8 times 9 would give you 72. And again, the reverse. 9 8s, 12 6s, 18 times 4, 24 times 3, 36 times 2, and 72 times 1. Again, that is a commutative property of multiplication that says the order in which we multiply will not change the product. Now for number 3. Number 3 says find the common factors for each pair, then write the highest common factor, or HCF. So now we're being asked to find the highest common factor of 20 and 36. So let's get these 20 and 36, and we could factorize these. So starting with the smallest prime, 2 into 20, 10, 2 into 10, 5, and 5 into 5, 1. Then 36, we could go 2 into 36 goes 18, 2 into 18 goes 9, 3 into 9 goes 3, 3 into 3, 1. So the prime factors of 20 would be 2 times 2 times 5. Prime factors of 36 would be 2 times 2 times 3 times 3. And we're going to look for what is common out of this. So 2 is common, so we'll keep this, and 2 is common, so we'll keep this. 5 is not common, 3 is not common. So our answer, the highest common factor, will be 2 times 2, which is 4. So the highest factor that 20 and 36 have is 4. And if we wanted to use a listing method to show this, what we could do, we could get the factors of 20. The factors of 20 are 1 and 20, 2 and 10, 4 and 5. And then 36 would be 1, 36, 2 and 18, 3 and 12, 4 and 9 and 6 and 6. Okay, let's look at the common factors first. The common factors would be 1, 2, 4. We don't have any other that's common, and the highest common factor in this setup, the highest common factor is actually 4. Okay, so the highest common factor would be 4. Now, instead of going through this listing process, which is longer, the faster way of getting it done is to factorize each number, then look for the pairs that are common, multiply those, and you'll get the answer. So again, the highest common factor of 20 and 36 would be 4. Now we go to 18 and 27. So 18 on one side, 27 on the next. And we're going to look for the highest common factor. So 2 could go into this. 2 into 18, 9. 3 into 9, 3. 3 into 3, 1. 27, 2 can go in there. 3 can go in there. 9 times 3, 9 is 27. 3 can go into 9. 3 times 3 into 3, 1. So the prime factors of 18, let's start with 18 and not 27. The prime factors of 18 would be 2 times 3 times 3, and 27 would be 3 times 3 times 3. Let's look for what is common. These are not common. These are common and these are common, so this would be 3 times 3. So the highest common factor is going to be equal to 9. So 9 is the highest common factor. All right, let's just look at this once again with doing our listing. So we have 18, we have 1, we have 18, and then 2 9s would give you 18, and 3 and 6 would give you 18. Then we have 27. We're gonna have 1 and 27, and then 3 and 9. Okay, so let's look at the common factors here, being 1, 3 and 9, and the highest common factor in this case would be 9. So again, this method is listing, and the other method here is using prime factorization. Next pair of numbers would be 54 and 60. Both of these are even, so we can start off with 2. 2 into 54, and this would go 27 times. Okay, 2 can go into 27. We go to 3. 3 into 27, 9. 3 into 9, 3 times. 3 into 3, 1. Let's go with 2 into 60. This would be 30. 2 into 30 would go 15 times. 3 into 15 would go 5 times. 5 into 5, 1. So the factors, the prime factors of 54 would be 2 times 3 times 3 times 3, and the prime factors of 60 would be 2 times 2 times 3 times 5. Let's look at what is common. We have 2 being common and 3 being common, so the highest common factor would be 2 times 3, so the highest common factor would be 6. Let's go next pair. We have 80 and 95. Let's get these. We're going to use 2 because this is even, so 2 into 80, 40, 2 into 40, 20, 2 into 20, 10, 2 into 10, 5, 5 into 5, 1. Then for 95, so 95, 5 into 95 would go 19 times. All right, because remember now, 20 sets of 5 or 5 sets of 20 would be 100, and 95 is 1 less, so it's 19. Now 19 we know is a prime number, so only 19 can go into 19, and that will go in 1 time, so we're done. So let's look at these. 80, the prime factors will be 2 times 2 times 2 times 2 times 5. Let's make sure 1, 2, 3, 4. 1, 2, 3, 4. Yes, by 5. And for 95, it would be 5 times 19. So the only things that we see common would be the what? The 5. Okay. So the highest common factor would be 5. Number 5 says express each as a product of its primes in exponential form: 100, 96, 84, 125, and 36. So let's move over to our whiteboard and let's look at 100 as a product of its primes. What we will have to do, we'll have to factorize each number, and when we factorize the number, then we go from there. So we'll have 100, and let's factorize 100. So 2 could go into this 50, 2 into 50, 25, 2 can't go in there, 3 can't go in there, 5 could go into 5, 5 could go into 25, 5 times 5 into 5, 1. So now 100 as a product of its primes would be 2 times 2 times 5 times 5. So 100 in exponential form would be 2 squared by 5 squared. Next number would be 96. Let's factorize 96. 2 could go into 96. This could go 48 times. 2 into 48 could go 24 times. 2 into 24 could go 12 times. 2 into 12 could go 6 times. Let's extend our line. 2 into 6 could go 3 times, and 3 into 3 could go 1 time. Then now we could say that 96, prime factors of 96 would be 2 times 2 times 2 times 2 times 3. Let's make sure we have those. 1, 2, 3, 4, 5 of them. So we're going to check now to see. We have 1, 2, 3, 4. Let's go 1, 2, 3, 4, 5 of them. So we need to make sure we have that. Let's clear that off. And we're going to write 5 times 3. 2 to the 5th power times 3. And 3 to the 1st power. And that's our answer for 96. So let's factorize 84. We're going to go with 2. 2 could go into 84 42 times. 2 into 42 21 times. And then we have 3 into 21 going 7 times, and 7 into 7 going 1. So 84 would be 2 times 2 times 3 times 7, and this would be written as 2 squared times 3 to the first power times 7 to the first power. Let's factorize 125. 5 could go into 125 25 times, because 5 into 12 would go 2 times, remainder would be 2, and 5 into 25 would go 5 times. 5 into 25 goes 5 times, and then 5 into 5 would 1. So the prime factors of 125 would be 5 times 5 times 5, and that could be rewritten as 5 to the third power. So again, 125, we're going to use 5. 5 into 125 goes 25 times. 5 into 25 goes 5 times. 5 into 5 goes 1. So the prime factors of 125 would be 5 times 5 times 5, and that can be rewritten as 5 to the third power. So last one we have is 36. So 2 into 36, 18. 2 into 18, 9. 3 into 9, 3. And 3 into 3, 1. So 36 as a product of its primes would be 2 times 2 times 3 times 3, or 2 squared by 3 squared. In this episode, we were able to look at factors and multiples, and we looked at the prime number Sieve. We examined the factor tree. We were able to find the highest common factor. We even looked at the definition of multiples. Now it's your turn. Go to that textbook and find the additional activities on factors and multiples. Complete those and turn them into your teachers. Now take care, and I'll see you in the next episode.